Hey folks, Ms. Gosling here. In this video, you're going to learn about the work-energy theorem. By the end of the video, you'll be able to solve problems involving the work-energy theorem. So let's go ahead and get started. And we're going to start by just defining the work-energy theorem, which is, I think, pretty self-explanatory from its name. What the work-energy theorem says is that the work done on or by a system is equal to the change in energy of that system. So we write that mathematically as our work in joules is equal to delta, which means change in energy, which is also measured in joules. Another way to write that is my work is equal to my final energy minus my initial energy. So one really good example of work that is changing the energy of a system is when you slam on the accelerator in your car or don't slam it on and you gently accelerate. Regardless, turning the gas on your car on is causing you to speed up. So the engine is doing work on the car, causing it to speed up. Another good example is if you pick up a heavy box or a light box and you lift it above your head, you're increasing the potential energy of that box and are there by doing work on the box. So let's go ahead and look at an example problem. How much force is required to lift a 10-kilogram box up 2 meters? So here's my box on the ground at height equals 0. Then I lift it up 2 meters to height equals 2 meters. And I'm going to have to apply some kind of a force to do so. So now that I have a picture, I'm going to go ahead and list out my givens. So I know that my initial height is 0 and my final height is 2 meters. I also know that the mass of my box is constant and is 10 kilograms. And of course, little g is 9.8 meters per second squared. Always a good thing to add. I know as well that my unknown is the force required to lift that box up. So, to solve this problem, I'm going to use the work-energy theorem, which states that the work done by a system is equal to its change in energy. Let me go ahead and expand that out. So I know that work is equal to force times displacement. So that means on the left side of my equation, I can write force times displacement. And on the right side of my equation, I know that the only energy I'm worried about here is potential energy because at no point do we have any movement. So since there's no movement involved, we know that kinetic energy doesn't matter, which means that the only thing we need to worry about is our potential energy. So our change in energy is our final energy minus our initial energy. And in this case, it's our final potential energy minus our initial potential energy. Now, what I want is for my equation to only include and let me go ahead and add displacement to my givens, which I forgot to do. But what I want is for my equation to only include my givens and unknown. So I'm going to go ahead and expand out my UG final and UG initial so that it's really clear where I'm going to plug my givens in the next step. So force times displacement is equal to mgh final, or my final potential energy, minus my initial potential energy, given by mgh initial. So now that I have an equation that only uses my givens and unknowns, I'm ready to sub and solve. Now, force is my unknown, so that means it gets to stay as a variable. My displacement is 2 meters. My mass is 10 kilograms. G is 9.8, and my final height is 2 meters, which I'm just going to go ahead and write in as 2. My initial mass is 10, G is not changing, and my initial height is 0. So now let's go ahead and simplify. So 2 times my force is equal to 10 times 9.8, or 98 times 2. And 10 times 9.8 times 0 is going to just go ahead and become 0. Now, you may wonder, why did I keep that 2 in there? Well, I have a 2 on both sides. So when I solve for f by dividing both sides by 2, my 2's on both sides will cancel. What I'll get is that my force is 98 newtons. Now, if you wanted to multiply 98 by 2 and then divide by 2, you could do that. I personally like to use these little math tricks to make the calculation a little bit easier. Regardless, no matter what approach you take, you'll get that the force required to lift that box up is 98 newtons. Now let's go ahead and look at a second example. I push a 750 kilogram car with a force of 100 newtons over 5 meters. How fast will it be moving when I am done pushing? How much energy did I use to move the car? So let's go ahead and start by drawing a picture. So here is my car, and I am pushing it with a force of 100 newtons over a distance of 5 meters. And my car has a mass of 750 kilograms. Initially, my speed is 0, and my final speed is the thing I want to find. So from that picture, I'm ready to go ahead and list out my givens. I know that my mass is 750 kilograms, the force applied to the car is 100 newtons, and the displacement of the car is 5 meters. I also know that my initial velocity is 0. From that, I can go ahead and list out my unknown, which is my final velocity. And I'm ready to write out my work-energy theorem equation, which is that my work is equal to my change in energy. Thus, my force times my displacement is equal to my final energy minus my initial energy. And in this case, at the beginning, we're going to be worrying about kinetic energy, since my car is moving it's moving horizontally. So that means that it's not going to experience a change in potential energy because its height isn't changing. However, we know its speed is changing because the question is asking me about a changing speed. So we know that it's going to have a change in kinetic energy. We also know this because it has to have some kind of a change in energy. And if its potential energy isn't changing, then it must be its kinetic energy that's changing. So force times displacement is equal to our final kinetic energy minus our initial kinetic energy. Or expanding further, force times displacement is 1/2 times my mass times my final velocity squared minus 1/2 times my mass times my initial velocity squared. Or if you want to use some of the terminology we used in previous units, it's going to be 1/2 mv squared minus 1/2 m times u squared. Whichever you prefer, either is fine. I'm going to go ahead though and write that this is also u, so that way it's really clear for y'all. So with that, I'm ready to sub and solve. So I know that force times displacement, or 100 times 5, is equal to my change in kinetic energy. So 1/2 times 750 times my final velocity squared minus 1/2 times 750 times 0 squared. So that whole final term is going to cancel out because anything times 0 is 0. Simplifying, this gives me 500 is equal to 375 times v final squared. Next, I'm going to want to divide each side by 375. Giving me v final squared is equal to 1.3. And then I want to take the square root of both sides. And what I will get is that my final velocity is 1.2 meters per second. So there you have it, guys. Here's yet another kind of work energy theorem problem. But the other question that I want to know is, how much energy did I use to move the car? So let's think about it. The car is gaining energy, right? And that energy has to come from somewhere. And what it's coming from is me. So the energy that the car gains is equal to the energy I used to move the car. So what that means is if I can calculate the final kinetic energy of the car, then I have found my energy used. So I know that the final kinetic energy of the car, and actually let's be a little more specific here. The change in energy of the car. So it's not really its final kinetic energy, it's really the work that I did. So the energy that the car gains is the energy that I used. Therefore, the work done on the car is the energy I used to move it. Therefore, work is equal to my energy output, which I'm going to call energy out. Therefore, my energy output is equal to force times displacement, 100 times 5, or 500 joules. And that is the energy that I used to move the car. So where does the energy come from? Well, the energy that I used to do work is energy that I'm losing. So if any of you have ever lifted something heavy, for example, so if anybody has ever done any weightlifting, or if you've gone for a run, that energy that you're using to move heavy objects or to speed yourself up is coming from the chemical energy of the food that you eat. So those carbohydrates, those sugars, those fats, those proteins inside of you are what is creating the energy that you can then output to do work. So you are losing energy in order to move your car. And that brings us to our takeaways. So first of all, when work is done on a system, it gains energy. And when a system does work, it loses energy. So our total energy in the universe is staying constant. But which system that energy belongs to, whether that's me or my car or a box, is gonna change depending on who's doing work on what. So with that, you now know how to solve problems involving the work-energy theorem. It is now your turn to give solving these problems a try. So best of luck and happy solving.